Hello snow leopards. Here we are on day 3. Your goal today is to go deeper to look at the elements that make up the molecules in your food. You should complete the following by the end of the period. Answers in your doodle sheet from I to L. Read a short passage on protein structure and annotate the big ideas. Watch the Amoeba Sisters video on biological molecules, as well as answer worksheet questions with your group on that same video. Watch the banana slug video and answer questions on your doodle sheet. First slide, here we are, going deeper on proteins, carbs, and fats. So what do molecules of protein, fat, and carbohydrates look like? Well, if you look at this model on the left, it is showing you what a protein looks like and how it's structured. Keep in mind this is just a model, so it's not at all what a real protein looks like. You can see for this model that there's a portion of it that's been stretched out, just to give you a sense of the actual structure of protein. So I want you to look at the pattern or the shape of this protein molecule and compare that to the molecule on the right that represents the carbohydrate. So there you can see the carbohydrates have a pattern to them, and how would you describe that pattern? One way to describe that pattern would be to call it a ring-like structure. Does that make sense if we would call it a ring-like structure? And now look at the fat molecule and look at how those individual atoms are structured together. So look at the pattern of the atoms in the fat molecule, compare that to carbohydrates, and compare it to proteins. This is one of the main differences between these three. Okay, carbohydrates are chains of sugar molecules. Sugars come in different forms, but all are made of the same basic parts. Carbohydrates, obviously being made of sugars, and the simplest of them are the monosaccharides. Mono means one, saccharides is the actual root for the word sugar. But the big star of the show for the carbohydrates is, do you know that? Glucose. So glucose is key, or one of the key carbohydrates, because all biological energy is originally captured from the sun by plants as glucose through photosynthesis. And every cell that needs energy uses glucose to get that energy through a process called respiration. So for right now, I want you to look at this chemical formula. And here we have the symbol for glucose. The C stands for what element? Carbon. The H stands for what element? Hydrogen. And the O stands for what element? Oxygen. For a molecule of glucose, for one molecule of glucose, how many carbons are in it? There are 6. And you can see at the picture on the bottom left, how many C's can you count? You should be able to count 6. For hydrogens in the molecule of glucose, how many hydrogens are there? There are 12. And again, on the other model of glucose to the bottom left, that little diagram, how many H's are you able to count? Should be able to count 12. And for oxygen, how many atoms of oxygen are in glucose? 6. And again, to that diagram on the left, you should be able to count 6. Go ahead and write C6H12O6, or the formula for glucose, in Doodle J. All right, what is in a fat? So our next subject, fats, lipids. There are many kinds of fat, but they have a common structure. And we're going to look at a type called a triglyceride. And you have probably heard about triglycerides before. Fats are mainly made up of two chemical ingredients, glycerol, which is a kind of alcohol, and fatty acids, which are really long carbon-hydrogen chains that end in a carboxyl group. So when you get three fatty acid molecules, those three fatty acid molecules marked in red together, and then you can connect them to a glycerol, that whole thing there is called a triglyceride. There's your C for carbon, there's your H for hydrogen, there's your O for oxygen. So notice what makes up fats: hydrogens, carbons, and oxygens. If you would write the chemical formula for fat, starting with the letter C, how many do you think you would have in there? Well, I'll go ahead and give it to you. It's 44. So in this whole triglyceride, there are 44 carbons shown, there are 86 hydrogens, and there are only 6 oxygens. Okay? Triglyceride. Go ahead and put the chemical formula for the triglyceride in your doodle box J under chemical formula. And then make sure that you write off to the right the elements that are present: carbon, hydrogen, and oxygen. Okay. Now let's go on to the different kinds of fats. For this first one, it's a saturated fat. It's solid at room temperature. What do you think the picture will reveal? Saturated fat and solid at room temperature. Why, it's butter. Now we've got an oil. So it's not a saturated fat, so what must it be? Unsaturated. And why is that? What's the difference here? The difference is in the being a liquid at room temperature. So the unsaturated fat is liquid at room temperature versus the saturated is solid. And then look at your carbon chain. And by carbon chain, I mean all of those C's in a row. Do you notice a difference there? Yeah, so in the unsaturated fat, you have this double bond there with carbon, versus in the saturated, you have that extra hydrogen. So that shows you a difference there. And then now we've got our third kind of fat. Any idea? It's the one that is the absolute worst for you. Trans fats, or hydrogenated fats. Okay? These are actually have been artificially made by people. It's when we actually force hydrogen atoms onto unsaturated fatty acids. So they don't have the hydrogen, but we force them in there, and that makes them these things we call trans fats. And these are just horrendous for your health. So donuts are fried in oil, French fries are fried in this oil. It's all this fried stuff, fried chicken, those are all have trans fats, and it's really bad for cardiovascular health. Bad for the heart. Okay. So let's just take a moment to clarify some words that we have been using. Okay, first off, matter. So you've already written about matter. I think the majority of you know what matter is. What would you say? What's your definition of matter? If you have anything that has mass and takes up space, give yourself an A+. Examples of that would be the desk, water, air, wood, plants, you, Lady Gaga. All right, the next word, elements. What's an element? I mentioned it earlier. I talked about C being carbon, that's an element. H being hydrogen, that's an element. Do you remember back in middle school when you had the periodic table? So what's an element? Can you name other elements besides carbon, hydrogen, oxygen? Well, elements are the pure substances that all matter is made of. And so basically, most everything in the world actually is a mixture of elements. But there are certain things that are truly pure, like gold, for example. So if you would take a chunk of gold and you would cut it in half, and you'd cut it in half and half and half and half, and to the tiniest piece possible of gold would be 1 atom of gold. We're going to continue on here. All known elements are shown on the periodic table to the right. I'm going to pop it in a second. Here are some examples: carbon, oxygen, gold, hydrogen. There is our table. So again, everything on this table is what makes up the physical world around us, which is kind of amazing because there are about as many elements on this table as there are keys on a piano. It's not too far off. So think about that. Even though we have this amazing diverse world and the universe, of course that includes our planet and solar system, everything, is some combination of the elements on this table. And it doesn't seem like that could be possible because it feels like it's too limited, right? But imagine this. Again, if the number of elements here are about the same as keys on a piano, well, how many different songs are there in the world? Wow, it's infinite, it seems. So just like the way you rearrange notes on a piano to make different songs and strike different chords, and there's every genre of music possible, same with these basic fundamental building blocks of matter that these atoms create in their amazing combination everything on our planet and in the universe. So again, an atom is the smallest particle you can have of an element. So 1 atom of hydrogen is the smallest piece of hydrogen you could ever have. 1 atom of carbon is the smallest piece of carbon you could ever have. And again, here are some of our examples: carbon atom, hydrogen atoms, oxygen atoms, gold atoms, etc. Calcium atoms, potassium. And now we have the word molecule. So what's the difference between an atom and a molecule? I'm going to give you a hint. Can you think of a molecule that you know? For example, H2O. Why is H2O a molecule and not an atom? Well, a molecule is simply 2 or more atoms bonded together, which forms and that got cut off a little bit, forms a new substance. So here are some examples. You've got O2, H2O, and CO2, carbon dioxide. So you got 2 or more atoms bonded together forming a substance. Okay, now I would like you to go to Google Classroom, click on the link for the Amoeba Sisters Biological Molecules video, watch that with your group, and write in the answers on your worksheet as you follow along. So make sure you pick up that worksheet and watch the video. Enjoy. Alright, now we're going back into proteins. You got a little sense of these different macronutrients that we're talking about with carbohydrates, fats, and proteins, lipids, and proteins. And now I want you to read about proteins. And you're going to write the big ideas from the reading in Doodle Box K. And keep in mind, I do know that you have not finished filling out the big molecule protein. We will come back to that. So go ahead and put me on pause, read the reading, and put in 3 to 4 big ideas from your reading and annotate it. All right, here we are back in proteins. If you have not done the reading yet, pause me now, make sure the reading gets done, and then we'll come back to this. Okay, so hopefully you've completed the reading and you've written your big ideas. And so let's talk a little bit more about proteins. Proteins are incredible. They are complicated, awesome chemicals in our body. Right now, there are tens of thousands of proteins doing everything they can to keep you alive. There are enzymes regulating chemical processes, helping you digest food. There are antibodies connecting themselves to invaders like bacteria and viruses so that your immune system can go out and get them. There's endorphins that mess around with your brain and that causes your emotions. They're everything. They're doing all this stuff. And again, what's kind of amazing, there's just 20 different ingredients, and these are the amino acids. So proteins are made from chains of amino acids. Here you have 3 amino acids shown in this chain. Protein is twisted and folded in on itself, as illustrated by this diagram. And each kind of protein has its own sequence, and it folds its own unique way. And again, there are millions of kinds of proteins. So proteins are chains of smaller molecules called amino acids, as we already talked about. If you look at the middle of this slide, it shows you that carbon is in the middle of the amino, and the acid group, carbon is in the middle there of the amino and the acid group. And it shares one of its electrons with a hydrogen, and the other electron is free to be shared with something we're going to call an R group. So it's this kind of fill in the blank thing that, like a side chain, and there are about 20 different kinds of side chains. And whatever that blank is, it's going to determine the shape and the function of that amino acid. Okay, I want you to go ahead and write these. This is where we're going back to Doodle J. Go ahead and write in these 3 chemical formulas for Doodle J. Also, before you do that, notice we've got a new element. How are proteins different from carbohydrates and lipids? I see nitrogen. So notice that we've got nitrogen in here for proteins, and we did not have that in the chemical makeup of carbohydrates or lipids. One other piece to look at on this slide is I want you to look at the bonds between these 3 different amino acids. So notice that they are bonded in multiple ways with that new nitrogen thrown into the mix. So that's another key point. Alright, so go ahead and put in these chemical formulas. I should go ahead and pronounce them though. So that first one up there is isoleucine. Kind of a fun word to say, isoleucine. The second one is the most fun to say, phenylalanine. 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 And then your last one, how do you think that gets pronounced? Glycine. And again, as you look at these formulas, right, just look at the ratios of the carbons, hydrogens, nitrogens, oxygens to each other. Those are all key differentiation parts among these different amino acids. Okay, go ahead and put me on pause and write in your formulas. Oh, one more piece. There's 20 different amino acids that make up the proteins in most living things. Here are 3 of them. I think that was supposed to be at the beginning. Anyway, let's go to the next one. Okay, proteins are made up of amino acids. It's getting a little repetitive, but hopefully this will be very memorable. So, as amino acids are linked via their bonds, the nitrogens, how many acids are there in the molecule? So let's look at the ends where nitrogen is, right? And so that means we actually have 4 amino acids, 4 shown in this diagram. And so we have valine, glycine, serine, and alanine. And just so you know, nitrogen is super important because this is the first time that we have nitrogen showing up in our food is in the proteins. And nitrogen itself is actually very abundant. Like 80% of the air around you is made of nitrogen, but we can't just pull it out of the air and put it in our bodies. So it doesn't do anything for us when we're breathing. But we have to get nitrogen from food. And so we have to eat foods that are high in protein, like eggs, because all that white part is protein, and it has a lot of nitrogen in it. Okay, so keep in mind here that this model of 4 amino acids isn't long enough to make a real protein, and they're typically like hundreds of amino acids long, but we've got 4 on this slide just as an example. Okay, now we're on to matter and molecules. Carbs, fats, proteins. What do these molecules have in common, and what are some differences between them? So again, we're looking at this protein, zooming in on an amino acid chain. Then we've got the fat molecule, and we've got the carbohydrate. So what are some things they have in common, and what are some differences between them? Please discuss this with your group. Alright, as you discuss this, go ahead and write your ideas about it in Doodle L. You can put me on pause and write your ideas about it in Doodle L. Okay, hopefully you said that all of these molecules are important because they have the same 3 elements. You can also refer back to your Amoeba Sisters video notes and add in any other commonalities or differences that you might find there. Alright, our last slide here, matter and molecules, carbs, fats, proteins. Do you have any other questions about vocab or anything else we've covered? If you do, please write your questions down. I am going to be trying to circulate around and pull you aside in chat, but it would help me if you write down any questions you have so that I can look over them and get back to you the next time we meet. Okay, so once again, revisiting that goal to go deeper at the elements that make up the molecules in your food, and hopefully you have all of these things complete and it all made sense today. All right, that's it for today. Good job.